Now it's time for something totally different, and it will be totally different, right? We're going to talk about how a mass might move on a spring as another system. So here's our little situation. Are you ready for the artistic showing of your life? Let's say we have some kind of ground, and something is on the ground, and we got a spring, and this attached to the spring is some object. Okay. And let's say here is the object at rest. That's going to correspond to a value of y equals 0. Y will be essentially how far from rest the object is. This is not a physics class, so we're not going to be very precise here. We're going to focus on the math. And then, of course, right, we could just stretch out the spring and, pull that to the right. And then as we release it, the spring will pull it back to the left. It will cross that equilibrium, or I spoiled it. It will cross that equilibrium point and compress, and then the compression is going to push it back, right? And of course, that's going to go back and forth. Now, specifically here, we're going to talk about a simple harmonic oscillator, otherwise known as an undamped harmonic oscillator. All right. And what we know about here is we know a few things from physics. And again, I'm not exactly sure your physics background, but there's this little guy called Newton who did some physics in his time. And he had a couple laws that he liked to talk about. And here's one of them, that the force is equal to the mass times acceleration. And there's this other guy named Hooke, all right? And not from Peter Pan, but a different kind of Hooke. And he also said that for a spring, the force is going to be negative, the constant, times its position. So, right, the further away we are from rest, the bigger the force is going to be acting on that object. So what we do is we combine these two things, right? And we say, okay, well, if force is this and force is that, then what I know is that mass times acceleration is negative some constant times y. You ready for it? What's acceleration, my friends? Acceleration is the derivative of velocity. Velocity is the derivative of position. Acceleration is the second derivative. So this is really just mass times the second derivative of the position with respect to time is equal to negative k times y. And by golly, what do we have here? We have a differential equation. Thanks, Newton and Hooke. All right. And a lot of times we rewrite this differential equation, especially when we're getting into second order differential equations. Because this is a second order differential equation, right? There's a second derivative. We really like having the coefficient of this derivative term equal to 1. So we're going to write this as second derivative of y with respect to t is equal to negative k over m times y. Or we oftentimes also just move everything over to the left. K over m times y over here. All right. You may see it in different forms, but here is our model for the simple harmonic oscillator. And again, simple sometimes is called undamped harmonic oscillator. And specifically, the reason why it's simple is we're ignoring a little thing called friction. All right. Realistically, it's going to lose some wiggle every time you release it, right? We've all played with springs, I think. I don't know. That would be a damped harmonic oscillator, and we will talk about that later in this chapter. Okay, so this is the simple version. Friction doesn't exist. You pull it and release it, it's going to go bong, 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 bong forever. All right. And this is the model that kind of governs that. Okay. So a few things about this. Specifically, we have a bit of something weird is happening here. I said that this was a system of differential equations. Does this look like a system of differential equations to you? No. This looks like one differential equation. It's a second order differential equation, right? There's a second derivative, but this does not look like a system. Well, just you wait. You know, I could, if I wanted to, say, ask you the question, what's the relationship between position and velocity? And what you would tell me is you'd say, well, Jason, the derivative of the position function with respect to time is equal to the velocity. And I'd say, wow, that's correct. And then I might ask you, what's the relationship between velocity and acceleration? You'd tell me that the derivative of the velocity is the acceleration. So you might say, okay, this is the acceleration. That's the derivative of the velocity. So you'd say, okay, dv dt is equal to negative k over m times, wait, this looks like a prime right here, but it's not a prime, right? The acceleration is negative k over m times y. Whoa. Do you see what we just did? Let this sink in. We had a second order differential equation. What do we have now? A first order system of differential equations. And we can do that with any nth order differential equation with this simple trick. Mathematicians hate them. Okay? We can turn any nth order differential equation into a system of n differential equations that are first order, just like this. Just say, well, something, let's make a new variable. Now, it's very natural to make a new variable with position, velocity, and acceleration, but in other things, you can make a variable for every rate of change and just turn it into something like this. Again, sometimes we have this on the left, sometimes we have this on the right. It really is application dependent. All right. So yeah, isn't that cool? It's a system of differential equations. So when I said we have another system, I really meant it. And we're going to see something a little interesting here. Again, this is a first order system. We're going to see something really interesting with this, another similarity to our predator-prey model, but you're going to have to wait until the next video for that. And we're pretty much just going to finish the video right now and talk about how it's a very common technique to be able to switch forms between these. Sometimes systems are going to be better. A lot of times systems are going to be better when we're trying to do analytic techniques. And then there's usually it's this version that's a lot of times better for some analytic techniques. And then this, writing it as a system really gives us oftentimes a lot more qualitative analysis, and usually we have better numerical techniques. But again, these are very wide sweeping statements. It's just like, think back to your calculus days, right? If you had, sometimes you wanted to write things with negative exponents, and sometimes things were easier to write like this. You just have to know that they mean the same thing. We can always get from one to the other. It's the same thing with differential equations, higher order, and systems of differential equations. So I told you chapter 2 was about systems of differential equations, and it is, but really it's also about higher order differential equations. So we get a little bonus on top of everything. But that's it for this video. We finished this section by looking at an initial value problem for this differential equation. Bye-bye.